For this final report project video, I will tell you about my results for the project Machine Learning Approaches for Collision Detection of Convex Shapes. In the beginning, I will tell you about the formulation of the problem, synthesizing convex shapes, and then I will tell you about approaches to solve this problem and the results I got during making this project. This problem is widely used in many cases, for example, during developing of three-dimensional engines, in games, or for autonomous car driving systems that have to detect collision as fast as possible. Let's formulate the problem. So we have two shapes that can have different number of points. In this case, it's A1, A2, A3, and B1, B2, B3, B4. And we have to give an answer, do we have the intersection between these two objects? So we can clearly see that on the left-hand side, we don't have the intersection. On the right-hand side, we have the intersection between two objects. We will consider only convex shapes. But what does it mean? That means that if we pick two random points on the shape, the line that connects them will lie inside the convex shape. So we can see that the shape on the left satisfies this property. In real cases scenario, we can always approximate the general mesh by the convex hull. But even if we can't, we can split the non-convex shape into two convex ones. Let's start talking about previous related work. For example, there is a well-known separation axis theorem that works in the following way. We try to find such an axis that will separate two shapes. It works in the following way. We construct the perpendicular to this axis and make the projection of these two shapes onto this axis. In case, if these two projections are not intersecting, that means that we don't have the intersection between two shapes. The problem of this approach is that we have to compute projections, compute edge normals, and check for overlaps for each possible axis. That gives us quadratic complexity, and in case when we have the very large number of points or very large number of meshes, this algorithm becomes impractical. On the other hand, we have very new approaches like differentiable collision detection for a set of convex primitives that solve this problem by minimizing the constant that we have to scale our objects to find one unique intersection point between two shapes. So that means that if this constant is greater than 1, we don't have the intersection. On the other hand, if this constant is smaller than 1, that means that we have to squeeze two objects to find one unique point of intersection. Hence, we have the intersection between two polygons. In the article, they considered different shapes, different alignments, and different configuration of the system. And the problem of such approach is that it is iterative approach, meaning that the complexity of the algorithm is not fixed. And let's start talking about methods and models I used in my project. First, and the most simple one, is fully connected neural network that consists of several dense layers. The second one is recurrent neural network that allows you to recursively apply some transformation for each point of the shape. And finally, I considered the most advanced approach, transformers, that didn't show great results for my case, but it's still promising and I will continue to do research in this direction. Let's talk about how to generate data. In our case, it's straightforward. The first variant is to consider only regular convex shapes. That means that points are distributed on the circle. As we know, all linear transformations can be decomposed by using SVD. That means that any linear transformation of this shape contains rotation, scaling, and rotation. By producing random rotation, scaling, and rotation, we will make various regular convex shapes. And here is the example of this approach. We can see that we have many regular convex shapes. And then I used Python library that allows you to recognize do we have the intersection between two polygons to generate the data set. On the left hand side, we can see many examples where two shapes are overlapping with each other. On the other hand, from right hand side, we can see that there are many shapes that are not intersecting, but indeed they are very near to be intersected. So the data set will be very general and very diverse. So let's consider how multi-layer perceptron works. We have the following architecture. Let's say we have two shapes. Each shape consists of several points, and we can flatten this point into one-dimensional vector. Then we do this for each shape and can cut the resulting vectors. And then we apply several dense layers to get the final result, the probability of collision. I started my experiments with model of size 10,000 parameters. I used the cross-entropy loss to train this neural network. So you can see that the loss function decreases constantly, and then we come to the solution. And then I evaluated this model on the unseen data, and we can observe the accuracy of 85%. I increased the number of parameters from 10,000 to 250,000 parameters, and we can see that the final loss decreases and the accuracy increased to 90%. The second architecture that I want to tell you about is a recurrent neural network. Let's say we have a shape with n points, and then for each point we can apply the recurrent neural network cell, so we have the hidden state and the output, and then we apply the same cell to the next point, having the internal state of the previous point, and then we have the new output. We have the same procedure for each point, and finally we have the result for the last point. But how to obtain a fixed size vector? To do this, I applied the maximum along all of the components of the internal states. This approach allows us to concentrate onto the most important components of the output vectors. And then we apply dense vector, and we do this for two shapes, and then we concatenate the results for these two shapes, apply dense layers, and then we have the result, the probability of collision. This architecture has much smaller number of parameters than the previous one, and here is the result. We can see that the loss is the same as for multi-layer perceptron. Sometimes we have errors, and let's consider cases when we have incorrect results. We either didn't predict the collision or predicted it incorrectly, and we can see that even for a human it's difficult to detect do we have the collision here. So that's why the neural network is struggling in some of these cases. And here you can see the correct cases, and even if we have two shapes that are very near to each other, we can accurately predict the collision between two shapes. But of course we have to say that the accuracy is not 100%. We need to do further investigations to understand how to increase it. And finally, I did experiment with transformer architecture that is based on the attention mechanism. And here's the final architecture. It's very huge, and the first part of this network is just the producing of embeddings by applying the dense layer. Then we do the positional encoding, because we have to take into account the relative position of each point, and then we apply multi-head attention, then the dense layer. After that we combine results from two shapes and consider this as one object, apply multi-head attention. Finally we produce a fixed size vector by taking the maximum along all of the components, apply several dense layers, and finally have the result. Unfortunately, my experiments showed that this architecture is not very effective, and you can see from this slide, cross-entropy loss is stuck and didn't really decrease, and maybe that can be connected with some bug in the code, or the architecture is incorrect in some sense, and I'm still finding this solution for this problem, so I will have to do more investigation in this area to understand how to produce better architecture. But because attention is very promising, I think that this architecture can be very useful for solving this problem. That's it for my project. Thank you for your time.